Okay, so let me talk about the Maxwell-Boltzmann distribution. Have you heard about Boltzmann distribution? So many places. This is a very actually generic description about, this is a general statement. There is a sort of the energy, the higher you go, you have a less popular density. Or there's a less probability for you to change, find. So, probability for me to find, let's say it is for something with a V, we'll have a kinetic energy. Let's say the energy, kinetic energy. And the real statement on, let's say, okay, I'm gonna even going before the kinetic energy, just say in general, anything that has a different energy from the ground state and up, they are going to have this dependence of exponential energy divided by kT. It can be RT if you're dealing with energy per mole or energy per particle, you'll be kT. And typically they are used for the molecular level description, so they changed on R to K. It's the Boltzmann constant. So you start from very simple idea. The higher energy you go, there's a less population you will have. Yeah.
When you say exponent, you mean e to the
yeah. So this is to me e to the minus ek. So that's one. That's a problem. Yeah, it is a sharp decrease if you can start to know. The higher temperature you go, there is a less reduction. The dependence is less sharp. So essentially, this is a probability for me to find out. And the meaning of probability, for me to say, okay, I know I'm interested in the V, right? And the V has a kinetic energy, which is a mv squared, all right? So therefore, this will be proportional to, and then I'm going to say equal to certain k value, which is a constant, times e to the minus kt to mv squared. That should make sense to you. Right? So this is just saying that, okay, the gas has a moving and this kinetic energy, so I'm going to say that's an energy. This is the first portion of the equation. So there's a little bit more complex version that derives this equation. I'm just going to get a shortcut way. My note is more extensive than what is now, but this is a probability function. To have a meaning of probability, you should have a definition of, you need to do the integration of probability of V over entire possibilities. Okay? And that should be 1. That's just a definition of probability. Because I want to use it as a probability, and each gas molecule will have a different values of V, and then this is a whole integral. So I'm going to give a more complicated or complex version, which is, I think I can only define, let's just looking at the only one-dimensional value. I'm going to look at that. Okay. If I do this, I do that, the velocity can range from minus infinity to the plus infinity. And then this one is, I'm just saying, changing, only look at one-dimensional integration. So then I am actually confining my interest to the first portion, that is, this constant k is called a normalization. So we know these are proportional, but to make this function to be an integral to be 0, and that's the k value, has to be calculated. And you will have a very complex form. And the kx is m over 2 pi at. Okay. So this is to make this probability function to be has a mathematical meaningful probability. This is a normalized probability, so this function itself, with this normalization constant, it is going to be very useful. Okay. So from 1D to the 3D, what I am going to do, FV is expanded on 2. So it's an m over 2 pi at. What used to be a 1/2 becomes 3 over 2. And then this one is minus 2 at mv squared. And the v squared, once again, is x, y, and z. So this is in the 3-dimensional, that's the probability distribution function. Okay. So this function, if I draw this, that's a probability for me to find this is what I call, in the textbook it doesn't say, but I like to call this one as point probability. Okay. What I mean by point probability is, if I x, y, z coordinate, if this is a v, that's the v, they are different. Right? So if I'm moving at 100 miles, 1,000 miles this way, they are not the same velocity. So their probability is going to be like this, but in a sense, I do not care whether it's going this way or the other way. Right? I just want to know, there is enough moving gas in this room who's moving at 1,000 miles an hour. This way, that way, I'm going to count them everything to be the same. And that idea, I'm going to change it to what I call shell probability. All I need, so this idea, now I'm going to say, as long as they have within the same radius, I'm going to looking at within this shell. This is the one that I want to call this as a probability for me to find. Then this new probability function is f to the v. So this is something that I'm getting somewhere. Okay? I want to know, regardless of the orientation and the direction, as long as they have the same magnitude, then this is the function that I want. But this is just by definition, at any vector will have this probability, but I have a degeneracy, the one that has the same energy, and that one is essentially, what's the surface area of the sphere? Surface area of sphere? Do you remember that? 4 pi r squared? Remember that? Yeah, so what I need to do is 4 pi, for me the radius is the velocity, the speed itself, so v squared times, essentially, like something looks like that. Does it make sense? This is an important thing. This is essentially degeneracy. You know the word degeneracy? Do you remember that? The p orbital has a degeneracy of 3 same energy, 3 different orbital. Same thing here. Same speed, just a different orientation. They are different, I guess, a velocity. Yeah. But at the same time, that just a point me. I just do not. I want to know the actual the mass of this. So by looking at this, you will see this is a curve that we come a long way, and this is really the summarizing everything here. Okay, so I'm going to highlight. This is a 0. This is a velocity, and then the speed. And then this is a FV. Okay, and then I wanna know this, right? And then let me choose the 2 different colors, and then I will use it. Right? So let me draw this one, which is this, right? The bigger you go with a V, and this is a certain constant, right, at the temperature. So I can say this portion that is orange is just like this. Can you guys see that? This is actually another purpose of this PChem course. When you're seeing an equation, you start to develop the sense about what am I expected to see here, and this is actually quite redundant. I teach the polymer chemistry, the polymer physics portion. This one repeated one more time. Okay, so it's very similar. And if you look at that, this is just nothing but kind of exponential decay forms. And then I have this one, right? Do you remember your parabolic functions, right? So what do you have? You have a 0. Goes up like this. That's your 4 pi v squared, right? And this is your f point probability function, right? These are the 2 multiplying. That's the one that I can say the real f. And then this comes down to you see this one? And that is your one that I want to show. To remember this graph that in the beginning of the lecture that I was drawing, okay, you are seeing something looks like this, probability. This is what you see here. Okay? There are 2 components. One is a geometric degeneracy components and the point probability combined together. You got this more like makes sense. Right? There's a certain probability for me to find, and each gas molecule move at different speed. And I do have an exact mathematical function on this. And then, so I want to know what's my average speed. I want to know root mean square average speed. That's D, R, and S. And that can be just going to be very easy to calculate because we know this function, this is a normalized function, right? This is all normalized function, so I can really do the calculation. So you guys can look at the details of the calculation. I just want to show you the different types of the distribution. So once again, go here, speed distribution is a 0, going up, and down. Essentially, it's kind of asymmetric. Okay. Average speed. What do I do? I know that the probability, right? Probability multiply the quantity that you want to average. So if I want to do the average on V, let's say your V, and you do the integration from 0 to infinity. That's what the mathematics. This form will be repeated if you have you taken the micro PChem yet. You are not. You will taken it. This will repeat it many times. So if I want to average the value, all I need to do is this quantity that you want to average multiply by their probabilities. Right? This is the same thing that I have a 1 gram, 5 gram, 10 gram of different isotope, and then what's the probability? You multiply the probability, you sum together natural abundance, and that's your average value. This is the same thing. It's just a continuous distribution. So this is a quantity that you want to make an average, multiply by your probability, and do the average, and you'll get this one. Okay? So can you guys write down this in a form? Can you do that? Can I see you guys working on it? What do? I think, you know what, you want to write this way. I want to average on this, right? So you multiply by probability distribution, and you do all possible scenarios. That's it. Okay? And all you gotta do is, because this is not the unit of a speed, so they do the root mean square. So the whole unit is square root. Okay? And this one, what we call it has a name. So this is a V mean speed.